Ok, bonjour à tous. C'est mon plaisir de donner un talk ici. And I have been asked to speak in English, so I will gladly switch to English now. Thank you for the kind introduction. My affiliation was correct a few years ago, but now I'm working at the Johann Radon Institute for Computational and Applied Mathematics. No problem, I'm still a friend of RISC, and they are very close together, both in Linz, so no problem. This is an institute of the Austrian Academy of Sciences, so this is my affiliation. Okay, and I'm giving a lecture, an introductory lecture on this topic, creative telescoping for D-finite functions. Today, in the first part of the lecture, the main goal is to explain the title of this talk, to explain these two words, creative telescoping and D-finite functions. And I assume that you have no prior knowledge of this, so I will start from zero. Just to give you some motivation, why should we get interested in these kind of topics? I put a random collection of examples that after the end of this lecture you should be able to solve by yourself. So, for example, if you're working in combinatorics and you encounter sums of this type with binomials and other combinatorial objects and you want to evaluate them or prove identities of this form, then you can use these methods that I'm talking about. If you deal with hypergeometric functions and you want to evaluate them, here you see a particular instance of such an evaluation. This can be done with creative telescoping and even finding such evaluations. You can prove all kinds of identities among special functions. So here is a prototypical example where we see certain special functions. For example, here the Gegenbauer polynomials, the gamma function, the Bessel function. I will talk a bit about these. More examples, determinants. There is a variation of the creative telescoping approach that can deal with determinants. So here we have an infinite family of matrices. The dimension grows with the parameter n. The entries of these matrices are given by binomial coefficients, and you want, for each dimension, to have a closed formula for the determinant. This is given as this product formula, and you can prove it using creative telescoping. In physics, people are interested in Feynman integrals. Here is a very simple instance of such an integral. And the physicists are interested in, for example, in a recurrence for such an integral, and this can be provided with creative telescoping. And last example, again from physics, Coulomb integrals. So here we see an integral with two functions f and g involved, and they are defined with a complicated formula in the last line. And also such kind of things you can approach with creative telescoping. Another piece of motivation is a random survey of applications that happened in the past years of mostly people who are sitting here in the audience. So, for example, Aline Bostan, Frédéric Gissac, Marc van Hooy, Manuel Kauers, Lucien Pesch, they have done some work where they look at random walks in the quarter plane, and they study the generating function of such walks and express them as hypergeometric functions, and this was achieved using creative telescoping. Together with Aline Bostan, Sergei Yurkevich has recent work on the so-called Cunham's problem, which predicts the shape of biomembranes. And this result also heavily depended on a creative telescoping proof. Pierre Leres, Mark Metzaroba, Mohab Safieldin, all of them are here. They designed an algorithm to compute the volume of an n-dimensional compact semi-algebraic set, and also up to a prescribed precision. And also this has as one step creative telescoping. Here are some more. Miura Joldes with Bruno Salvi and other collaborators, they applied creative telescoping to compute collision probabilities in celestial orbits of objects in space. Jean-Marie Maillard, who's not here currently, with Alim Bostan, Youssef Abdelaziz, Salah Boukra, they study integrals that appear in physics related to the Ising model or lattice functions, lattice green functions, and we can say something about these objects using the method of creative telescoping. And one last thing, Vadim Sudilin is doing work in number theory, in irrationality measures of certain transcendental numbers, and also here he uses creative telescoping in the very same spirit as the proof of a priori, that zeta of 3 is an irrational number, can nowadays be achieved by using creative telescoping. Okay, so far for the motivation. I hope you're eager to learn about this and be able to solve all these miraculous problems. So let's start with some very basic things. I start with as the history developed, and this was hypergeometric summation. So let's have a quick look into this. And for this purpose, I have to define what is a hypergeometric term. F of n is hypergeometric if the quotient f of n plus 1 divided by f of n is a rational function in n. And this is called hypergeometric because it's a generalization of geometric sequences. A geometric sequence is a sequence where the quotient of two consecutive members is always a constant. And here it's a rational function. Okay, this should not have been here. Now I want to do a little quiz. And okay, so the first answer you see already. So let me see. And I want to try this tool. So everybody has a laptop open or a phone. So you can open this page. Because if I ask, nobody dares to raise the hand. You go to this page and you enter this number. Okay, and then you should see these expressions and have the possibility to choose your opinion, which of them are hypergeometric and which are not. Actually, you should tick those that you think are hypergeometric, and you don't tick those which are not. Okay, does it work? Yes, the first answers pop up. Maybe I should not show them to not bias you. You see? Oh, but only after you vote. No? Okay.
You can select just one.
You can say, okay.
A is a rational number?
What do we know about A?
A is whatever. Okay. Good. So everybody has seen the green tick already. So number 1 wins. Okay, and and that's interesting. Nobody thinks that this one is?
We can vote for only one.
Yeah. Okay. That's not good. That's not good. Yes. Okay. Yeah, it was. I tried it and it was not working. So anyway, I changed it and then it's messed up. Good. Then let's do it like this. Okay. So the first one. If you take the quotient, well, you get 3 to the a, and with respect to n, this is a constant. So in particular, it's a rational function in n. Well, the second one, we have a quadratic term in n in the exponent. So if we take the quotient, something like 2 to the n will be left, and this is not a rational function in n. So, okay, I go in this direction. Okay, let's do this first. Here, if we shift n by 1 and then we take the quotient, then these things are not going to cancel away and we are not left with a rational function. So this is not hypergeometric, and similar, this one is not. Here, I should say this notation in the numerator, for those who don't know, this is the so-called Pochhammer symbol that is defined as a sub n is a times a plus 1, a plus n minus 1, so the so-called rising factorial.
But for this one, I mean, if a is equal to 1, then it's hypergeometric.
Well, if a is 1, yes, then yes. But for a symbolic, it is not. If you replace a by any integer, it is hypergeometric. That's correct. But for symbolic a, not. Okay, and so here, yes, this is the Pochhammer symbol. Here, pi looks suspicious, of course. That's maybe why nobody crossed it. But if you look, what happens if you shift n plus 1? Well, then the whole, well, here you have the pi. This doesn't really hurt. The whole thing shifts a bit, and the gamma function is also fine. So this one is hypergeometric. And the last thing, well, we have a binomial coefficient and we have factorials with integer coefficients here, so no problem. Also, this is hypergeometric. Okay, good. So we have clarified this. Let me come to Gosper's algorithm. This is the first big step in symbolic summation. So here you see a picture of Gosper and this paper from 1978, decision procedure for indefinite hypergeometric summation. So what is Gosper's algorithm about? We are given a hypergeometric term, similar to what we have seen here. And let us call the quotient r of n, this rational function. And this algorithm answers the following question. Does this hypergeometric function f of n have a antidifference g of n? And by antidifference, I mean what is written here. Gn plus 1 minus g of n. Can we write f in this form where Gn is again a hypergeometric term? And this is very similar to the indefinite integration problem where you look for an antiderivative of a given function, right? A function whose derivative is your integrand. And similarly, here we use this to do summation. So if we have a sum, we want to sum f of n, and the upper bound is arbitrary, then we can use such an antidifference. So we plug it in, and then the sum telescopes, and we get a closed form evaluation as a hypergeometric term minus a constant. Okay, so this is very nice, and we see this is an important, very fundamental problem. Okay, so now let's look how the algorithm works. Assume such a G exists and we claim that it must be hypergeometric. Then it is easy to see that this G is not only an arbitrary hypergeometric term, but it must be a rational multiple of f. just take this equation here, divide both sides by g of n, then we get here the quotient f of n divided by g of n, and here we get this quotient, and by assumption that g is hypergeometric, this is a rational function, so the whole right-hand side is a rational function. So we can make the following ansatz. We can say g of n is y of n for some unknown rational function y times f of n. And the purpose, the goal is to compute this unknown rational function y of n. Okay, so we keep this in mind. We want to find this y of n such that g of n is an antidifference of f of n. So now we plug this in, we get this. Okay, no magic here. And now we divide this equation by f of n, then this disappears here, and here we get f of n plus 1 divided by f of n, which is a rational function that we called r of n. So our equation now looks like this. And if we have some knowledge about how to solve such difference equations for rational functions, we could stop here and say, okay, now we give this to a solver that computes us all rational function solutions of this difference equation, and well, either a solution exists or not, and we are done. But Gosper actually did a bit more. He thought about how to solve this equation. So as I said, we have now simplified the problem from computing a hypergeometric term to computing a rational function. And so the key idea in Gosper's algorithm is to write the certificate of f. So the certificate is this rational function that is given as the quotient of f of n plus 1 divided by f of n, to rewrite this in a very special form. So this r of n, we want to write it in this so-called Gosper form. That is a quotient of polynomials a of n divided by b of n, and then another polynomial c, which appears shifted in the numerator and unshifted in the denominator. Subject to certain GCD conditions. Well, here in the first line is just the trivial, I would say, conditions. So of course we don't want that a of n and c of n have something in common, and similarly we don't want that these two things have anything in common. But the crucial point, the important condition, is the last one, the blue one. So if we look at the first fraction here, we claim that any shift of the denominator has nothing in common with the numerator. So b shifted by whatever I, non-negative integer I, has no non-trivial GCD with a. And somehow this corresponds to extracting a polynomial from the hypergeometric term. So we want to write our hypergeometric term f that we want to sum as a polynomial times another hypergeometric term that has a certificate, a rational function that is as simple as possible. This is achieved by this Gosper form. And so if you can start by just writing this rational function, and for example in the first approximation you put everything into the a and the b, and then you check this condition. If you find that it is violated for a certain index I, then you just move certain factors from a and b into c. Right? So if you have something that is in this GCD, then you can move it into c. Maybe you add all the factors up to that point, and you can move all this stuff into the polynomial c of n. So there are algorithms to compute this Gosper form. I don't want to go into detail, just believe me that this is always possible. And if you make these polynomials monic, it's basically unique. Okay, now we take this Gosper form of R and we plug it into our equation here, into our difference equation for the unknown rational function y. And of course we clear denominators, and then we get this equation. Okay, remember this equation? No, you don't have to remember. It's here again. So now how do we continue with this equation? And here comes the ingenious idea of Gosper, that he realized that certain things go well together. Like here we have y of n plus 1, c of n plus 1. Here we have y of n times c of n. So he realized that this whole equation simplifies if we do a substitution. So we make y of n, we write it as b of n minus 1 times x of n divided by c of n. So the b and the c, these are known, and x now is yet another unknown rational function. And if we make this change of variables, the above equation simplifies, and you see that it can be obviously simplified even more by dividing out the b of n that is now everywhere. So we get this nice equation. And not only is this equation simpler than the original one, it has a very distinctive feature. So this is called Gosper's equation, and the true miracle happens now. Namely, so far we made this rational change of variables, and we say, well, x of n, this unknown function that we are now looking for, is a rational function. But under the assumption that we do everything according to what we have done, one can show that actually this x of n must be a polynomial. This is the true miracle in Gosper's algorithm, that you can by this change of variable, not only you predict the denominator of this unknown rational function y, also you predict, so this is the c of n, also you predict part of the numerator, a certain factor of the numerator, the b of n minus 1. And what is left is a polynomial x of n that now we have to look for. So recall, we have reduced the problem from first finding a hypergeometric solution to finding a rational solution to now finding a polynomial solution of a certain equation. Okay, every lecture should have a proof, so let's get around this. Prove this statement that is not too complicated. So let's assume to the contrary that x is a true rational function with a numerator and a non-trivial denominator q of n. Then what happens? Well, we plug it into the equation. So you see here the x of n plus 1 becomes p of n plus 1, and the denominator we multiply to all the other parts. And similarly, from this x of n, we get here this p of n, and the q of n goes everywhere else. So this is now our equation. Now let's see what happens. We define L to be the largest integer such that the denominator of this imaginary denominator of this x has a non-trivial GCD with its else shift, right? So this always exists, and potentially it is 0, right? If there's no non-trivial shift, but then if you assume q of n is a non-trivial, non-constant polynomial, then at least L equals 0 works. So we assume this GCD is a non-trivial polynomial, and therefore let's take an irreducible factor of it, call it u of n. And now what happens? So if u of n divides this GCD, that means u of n divides both of them, and if we shift it, then it divides, if we shift L backwards, then it divides q of n. Okay? So q of n is here, and it is here. Therefore, this u of n minus L must divide this part here. And now you can think a bit that un minus L can neither divide P of n, because we assume that it divides Q of n, and of course we assume that P and Q are co-prime. It's not written here, but it's somehow clear. And it can also not divide this Q of n plus 1, because we assume that L is the largest integer such that this has a non-trivial GCD. So therefore, this un minus L must divide the Bn minus 1. Similarly, we look at u of n plus 1. By this condition, u of n plus 1 divides q of n plus 1, which is contained in these two parts. Therefore, u of n plus 1 must also divide this part. And by a similar reasoning, we can argue that, well, u of n plus 1 is not allowed to divide p of n plus 1 and is not allowed to divide q of n, both latter because of this assumption on L, and therefore u of n plus 1 must divide a of n. And now we get the contradiction, because the existence of such a factor that divides both a of n and b of n minus 1 contradicts the assumption on the Gosper form. So recall, if we go back, no, here. So it is a contradiction to this blue formula. Yes. Okay, proof finished. So now we can continue without any proofs. So we are left, so now we have proven that actually this x of n is a polynomial. Now the only question is how to find it. So this is not too difficult. This is like in many cases we find polynomial solutions. We make some reasoning that we can bound the degree of this polynomial. This is some details that I don't want to explain now, but you get a degree bound, then you make an ansatz and you solve a linear system. And either this linear system has a solution, then you have solved this summation problem, or it does not have a solution, and then you have a proof that this sum cannot be, that your function that you started with does not have a hypergeometric antidifference. So it's really a decision procedure. Either you get an antidifference or you get a proof that no such antidifference exists. Okay, so here are examples that you can do with Gosper's algorithm. And you know, if you don't have this algorithm, I think it's not so easy to come up with these evaluations. And let me do a short demo, because of course these algorithms are implemented. Here is, I'm working in Mathematica, but in all other reasonable computer algebra systems, you have implementations of these algorithms because they are so classic. Meanwhile, so I use this implementation by Paule and Sean. And so if we input this, is this big enough? Yes. If we input this hypergeometric term, and we call the Gosper command, then you see in the output it tells you this hypergeometric term can be written as delta k is the antidifference operator of that what is written here, and then if you simplify this a bit, you get exactly the evaluation that was on the slides. Well, and if we put k factorial, this is somehow one of the simplest examples where it does not work. You get here the empty output. And this means this k factorial does not have a hypergeometric antidifference. And the same is true for the binomial. Okay, so conclusion is Gosper's algorithm decides the indefinite hypergeometric summation problem. Given f, find an antidifference g, which gives rise to an evaluation of a summation over f of k. Of course, we want to do more, and we ask, what about definite summation? So if the summand also depends on the summation bound. Or otherwise stated, if this sum only has a nice evaluation if the bounds are very specific to the problem. While here, well, this n has nothing to do with the f of k, so you can put arbitrary n, and then always you get a evaluation, right? So it's like an integration. You can ask for, if you compute an integral, well, in school you learn that one way to do that is find an antiderivative, and then you can evaluate your integral. But for many integrals, you don't find a nice antiderivative, but still you can evaluate the definite integral. So something like this. This is one of the simplest instances. Sum over the binomial coefficients is 2 to the n. Everybody knows this. We want to solve such problems. And we just have seen, so the binomial coefficient is not Gauss-Bass summable. So with Gauss-Bass algorithm, we cannot solve this problem. So for this one, we need something else. And this is now the second section of this talk is about Zeilberger's algorithm. And to do that, we have to talk about bivariate hypergeometric terms. So now we have f that depends on n and on k, and we say it's hypergeometric with respect to these both variables. If both shift quotients, both with respect to n and with respect to k, are rational functions in n and k. And again, we do a little quiz. So here you see 4 examples that I came up with, and I ask you to take a second. And let's not use this tool because it doesn't work properly. Just let's discuss it live. So for which of these expressions does it hold that both shift quotients are rational functions in n and k? The first should be good because it's very similar to what we saw before. Before we had 3 to the a times n plus 1, and no, I'm very mean. I try to cheat you, to trap you. Because, and there we argued, well, if we shift n, we get as a quotient 3 to the a, and this has nothing to do with n, it's a constant, so we are fine. Now we have n times k, so if you shift n, we get something like 3 to the k, which is not a rational function in k. Now the quotient must be a rational function in n and k, and either way we shift, this is not the case. So the first one, unfortunately, is not. Now n squared plus k squared factorial. Any idea? I mean, I see the experts already. Again, no, unfortunately, is not hypergeometric. If you shift, then you get n squared plus 2n plus 1 inside the factorial, and yeah, no, it doesn't work. N to the power k. Well, if we shift k, we get n to the k plus 1 divided by n to the k. We get n, this is fine. But if we shift n, we get n plus 1 to the power k divided by n to the k, and this is not. And the last thing, of course, you see how mean I am. I put a very complicated formula, but among all those, this is actually the simplest one, because here nothing goes wrong. We have a binomial coefficient, we have integer linear terms in n and k, we have gamma functions, and also there's this ugly pi and 1/2. It doesn't matter, this is fine, this is hypergeometric. Okay, good. So now we know what bivariate hypergeometric terms are. Okay, and before I go into Zeilberger's algorithm, I should tell you that actually Gauss-Bass could have solved such problems, but somehow he missed this opportunity. So let's assume we have a summation of a bivariate term, f of n k, and let's assume that this evaluates to some hypergeometric term h of n, like what we have seen in the example. Sum of binomial n choose k is 2 to the n. 2 to the n is a very simple hypergeometric term. So hypergeometric means we have a quotient of polynomials. And here we do some technical assumptions. So you see here I write sum over k. I don't care about the boundaries because for the moment I assume that this sum has what is called natural boundaries. So think of this f of nk to be something like the binomial coefficient that is non-zero in a certain range, namely from 0 to n, if you consider k, and 0 outside. So you can say I sum from minus infinity to plus infinity. And so we want to assume this for the sake of simplicity. How can we use Gauss-Plus algorithm to solve this sum? Well, we rewrite this equation for h, and then we plug in the sum for h. So we get here this sum and here this sum. So next we pull out the sum and we get this equation. So we now have a new identity, namely if we sum, instead of originally we want to sum over f and k, but if we sum over this guy, we expect to get 0. Yes? And well, and this is something that Gauss-Plus can do. We can apply Gauss-Plus algorithm to this complicated looking summand. And if we are lucky, we find a G that is an anti-difference of this summand. So it's G shifted k plus 1 minus G and k is this expression. Well, and now if we sum over this identity, and since G must be a rational function multiple of the summand, which, by the way, is a rational function multiple of f n k, because here you see f n plus 1 k, by the assumption that it's bivariate hypergeometric, is a rational function multiple of f n k, and therefore this whole expression is a rational function multiple of f n k, and equally it is the case for G, so it has finite support. We can sum over the whole thing and we get 0 on the right hand side. So we find that the sum satisfies this difference equation. Well, and this is nothing else than the difference equation for the right hand side. So if we now test that the first value at n equals 0 agrees, you have a proof that the sum over f indeed evaluates to h. So this you can purely do with Gauss-Plus algorithm. Let's look at an example. Let's now do this example that before we were not able to do. So now we want to do this one. So that means first we have to write down the difference equation for h. That here is very simple. H is 2 to the n. So we have h of n plus 1 minus 2 times h of n equals 0. We now plug f into this equation. So we have here the binomial coefficient, n shifted by 1, minus 2 times the binomial coefficient, and okay, we do some simplification. And now we feed this into Gauss-Plus algorithm. Let's do it. So here I copy this expression. Let's apply Gauss-Plus algorithm, and you see here we get the solution. Okay, we get this expression. So let's go back to the slides. Here, this is this expression. You can simplify it a little bit, getting a single binomial coefficient, and we see now that this indeed has finite support. So we get it. We find that the sum satisfies this simple recurrence equation, and okay, you have to check the initial condition, and you are done. Okay, so this was a little detour. Now let's really come to Zeilberger's algorithm. Here's a picture of Doron Zeilberger with his favorite T-shirt, where he writes such an identity and who you're gonna call. Yes, and here are two of the main papers where this theory is explained. A fast algorithm for proving terminating hypergeometric identities and the method of creative telescoping. So this I want to discuss in the next few minutes. So creative telescoping in general, it is a method that can deal with sums and integrals. And the important thing is that they must be parametrized. They must have a parameter, like the n we had in the sum before. And also important is that this method does not automatically give you a closed form evaluation of your sum, but it usually gives you a difference equation, a recurrence equation that is satisfied by the sum. But for many applications, this is as good as a closed form. You can compute values for the sum. You can study asymptotics. You can prove a given evaluation by showing that this evaluation satisfies the recurrence. So you can do many things with a recurrence. But of course, it's not, for some applications, it's not as nice as a closed form. And so this became popular in the past 30, 35 years. So let's look at an example. So here's an example of a sum. Everybody knows this sum. Everybody knows what is the result. So can we prove this by creative telescoping? Well, if you read carefully what I write, no, because we can only do parametrized sums. This sum does not have any parameter. It evaluates to a constant. So with creative telescoping, you can do nothing about this sum. Sorry. So let's introduce a parameter. So I take the same sum, and in the denominator, I introduce the n. Then this is something you can deal with. And also this is a classic sum that can be written in closed form using this the gamma function. But as I said, you should not expect automatically from creative telescoping to get this answer. But instead, what creative telescoping gives you is such a recurrence equation for the sum, not the closed form. So here, second order recurrence. And if your software has a good recurrence solver, maybe you then can get this closed form as a solution to this recurrence. Okay. So how does creative telescoping work schematically? So we look at the summation problem of this form. Now f and k, it can be whatever. And we want to sum it in a certain summation range. And we call with capital Fn the sum. In Gosper's algorithm, we have already seen the telescoping trick, and that every first semester student learns. So if we succeed to rewrite f as an antidifference that we have studied before, then we have an evaluation of the sum. Then we just evaluate this antidifference at the boundaries of the sum. But now let's assume that we are not able to find such an antidifference. Now comes the creative part. And the creative part means instead of studying the original summand, we look at a certain linear combination. We somehow give more freedom to the problem by introducing undetermined coefficients here, C0 of n up to Cr of n, and here we have shifts of f. So we have now many possibilities to create new terms by choosing these C's, and we can hope that a certain choice will be successful so that this new expression has an antidifference. So for the moment, let's not talk about how we find these C's. Let's just now assume we have found a certain R and coefficients C0 up to Cr, such that this linear combination can be written as an antidifference. Well, then the only thing we have to do is we have to sum this equation over k, which means that since on the left-hand side these C's do not depend on k, we can move these things out of the sum. And then we sum here f of n plus r. So that is our sum f of n plus r. And so on. Well, and here again on the right-hand side, everything telescopes. We get something nice. In many cases, this is even 0, so it's even nicer. But even if it's not 0, it's nice enough. And you see what we get is a recurrence for the sum. Now, the very same trick you can play with integrals. So now you have to look very carefully to my animation. Oh, wow. So you see, nothing changes. Well, not nothing, something changes. Sigma becomes integral sign. N and k become x and y, but this actually doesn't matter. Here, instead of antidifference, we find an antiderivative. And okay, here in this line is just the usual fundamental theorem of calculus. And here now you look for a linear combination of derivatives of f when you take the derivative with respect to the first variable, to x. And you assume that you find these coefficients such that this thing has an antiderivative. Then you integrate this equation, and what you get is a differential equation that is satisfied by your integral f, capital F of x, with a possibly inhomogeneous right-hand side. Okay? On the previous slide, this f could have been anything, but now let's restrict again to hypergeometric terms. And so we want to find, given f and k, we want to find such a creative telescoping relation, where on the left-hand side we have a linear combination of shifts of f. When we shift in n, and we have coefficients that depend only on n, so on the left-hand side, nothing is done to the k, and the k does not really appear. And on the right-hand side, we have an antidifference with respect to k.
Just one question with respect to the previous slide. It's called Feynman because Feynman came up with this method for...
Yes. So he has this nice book. You must be, what is the English title? You must be kidding or joking. You must be joking, yeah. Sie belieben wohl zu scherzen, Mr. Feynman. I only know the German title. And there he describes that he learned one trick to solve integrals, and that somehow nobody else knew. And so whenever somebody could not solve an integral, they came to him, and he was in many cases able to solve them. And when you read carefully, what he does is basically this, differentiating under the integral sign. So this is a funny story, falls under trivia. Now the question is, for this antidifference, where should we look for? Should we just say, well, wherever you find such an antidifference, you're happy? That we should not do, because, well, they are trivial solutions. If you look at the above equation, you just define g and k to be the sum over this thing, and then it will trivially satisfy this equation, and well, this doesn't give you anything useful. So this problem only makes sense if you restrict the search space for which you look into for the G to a reasonable set. And similar to Gosper's algorithm, in this world of hypergeometric terms, we want to search for a hypergeometric G, and by a similar reasoning, this is, if such a G exists, then it must be a rational function multiple of f of our given summand. Now, Zeilberger's algorithm. Well, so I told you that we could use Gosper's algorithm if we know what the sum evaluates to. Then we can actually do this trick and use Gosper's missed opportunity. But, well, often enough we get a sum and we have no idea what it evaluates to. And maybe it doesn't evaluate to anything nice, and we can just find a big recurrence for it. So what do? This is now solved by Zeilberger's algorithm. Again, let's assume that f has a finite support, so the sum has natural boundaries. And so now in theory you can show that every such sum, where f is hypergeometric and natural boundaries, satisfies a recurrence provided that certain technical assumptions hold. And the technical assumption is that f and k is what is called a proper hypergeometric term. I skipped the definition. It's not really important. It's a small condition on the f and k. So we want to find the recurrence for this sum. The problem is we neither know what is the order of this recurrence, nor do we know its coefficients. And so the strategy is that you try orders starting from 0 and you increase until you find something, and because of the theory you're guaranteed that at a certain order you will find a solution, so your algorithm will terminate at some point. And about the coefficients that we don't know, recall in the Gosper's algorithm we should provide the coefficients to feed the modified expression into Gosper's algorithm. Now we don't know the coefficients, so we have to do an ansatz with undetermined coefficients. So these P0 up to PR, they are now unknown, well, polynomials or rational functions. Yeah, we should say rational functions, but in the end, of course, you can make them polynomials if you wish. So we write the recurrence with these undetermined coefficients, and then we apply Gosper's algorithm to this, but we have to use a variant of Gosper's algorithm that takes care of these undetermined coefficients. So it's called a parametrized Gosper's algorithm. And this works as follows. So this is just a copy from the previous slide. Now you can do a careful analysis of, now you apply Gosper's algorithm to this expression, and you have to do symbolic calculations because you have these pi everywhere. But if you do this calculation that I save you now, because we have already done a proof, we don't have to do a second one, you find the following. First of all, the algorithm works. There's no obstacle. And in the end, when you do this, you compute this Gosper form, you write the Gosper equation, all this that I explained half an hour ago. Everywhere you have this pi, but actually you don't have them everywhere, but you will find that these pi, these unknown coefficients, appear only in the polynomial c. So in the Gosper form we had a divided by b and c of k plus 1 divided by c of k. And the pi only appear in the c. So here is Gosper's equation, so that means they only appear in the right-hand side of this equation, not in the left-hand side, which is very good because now, recall how we solve this equation. We find a degree bound for this polynomial x. We make an ansatz for the polynomial x. So we have these powers of k, and the coefficients of this polynomial are rational functions in n. So what our unknowns now are these xi, the coefficients of the polynomial x, and the pi. Well, and the xi are on the left-hand side, linearly, of course, and the pi are on the right-hand side of this equation, again linearly. So this whole thing reduces to a linear system of equations in the unknowns xi and pi that we can solve simultaneously for all these unknowns. And then either the system does have a solution, then we are happy and we can finish. If not, this means our ansatz with the order r was too small. We have to increase it and try again. And the general theory guarantees us that after a certain number of steps, this process will come to an end.
What's d here in the sum?
Well, this is the degree bound for the polynomial that we find somehow by analyzing the degree of a and b. You get certain conditions on the degree of x and the degree of c. There's a case distinction. It's a bit technical, but it's not really difficult.
So, but it's fixed or guessed?
No, it's not guessed, but you have to concretely. So when you run this algorithm, then a of k, b of k, c of k, they will be concrete polynomials with certain degrees and with certain leading coefficient, and then you have to investigate them and you know, you just check what is the condition on x so that the whole equation can be satisfied and you get a certain d. Yeah.
Speaking of guessing, we could guess the coefficients and then apply
That is correct, yes. So the question, I repeat, it was in the, we could actually do what we did with Gosper's algorithm before if we guess the coefficients of the recurrence. So we can just take the sum, evaluate it for n from 1 to 100. We get a sequence of numbers. We can use guessing to find the recurrence and then take these coefficients and feed them into Gosper's algorithm. That is indeed a possible way of doing it. And then you have if it works, you have a proof that your guess was correct.
What do we know about the xin as rational functions? Do we know the degrees of the numerators, of the
No, not well. You can derive bounds if you want, but you don't really need, because when I say a linear system, I mean a linear system over the field of rational functions in n. So we compute over k of n, and so in the end we get something, and yeah, we don't have to know.
So we don't associate those rational functions with coefficients. We just compute over as unknowns.
Right. We don't make an ansatz for the xi of n. They are just as such. And then in the implementation, of course, maybe you want to do evaluation, interpolation, or something like this. But this is technical details that are not relevant at this level. Okay, and so by construction, because we loop over the order of this telescoper is the name for the recurrence on the left-hand side here. So if we find, wait, let me, yeah, anyway. So this recurrence, this is called the telescoper, and because we loop, we are guaranteed to find the telescoper of minimal order. Good. So now let's look at some examples. Here. So again, in the same package, that was actually called fast Zeil, and it has Gosper as a subroutine, but the main thing is Zeilberger's algorithm. And if we put the most simple example, the binomial coefficient, you see in the output you get this recurrence, f of n plus 1 equals 2 times f of n, and so this implies the evaluation 2 to the n. So this output tells you that this linear combination can be written as an antidifference where f is here this input. Well, in my slides this is the lowercase f, and r kn is this rational function such that the antidifference is this rational function multiple of f, which is not shown explicitly here, but if you want to see it, they can do this command and it is shown. It's this simple rational function in this instance. Okay, and well, then we have other examples here. We have binomial 2n choose n plus k squared with an alternating sign. And again, this works. We get also here a first order recurrence, which means this is the second identity here, that you get a closed form evaluation as a hypergeometric term. Next example is the a priori sum with these two binomials squared. And here we see an instance where the recurrence that we get is not first order, so we don't have a nice closed form for this sum, but we can just say it satisfies this second order recurrence. And the last example, well, we have seen in our hypergeometric quizzes that for symbolic d, this is not hypergeometric, but if I instantiate d with some integer, this is hypergeometric. And so for any integer d, this has a very nice evaluation. Now let's look. So this is this expression. Here I choose d equal 2, and I get here this first order recurrence. This is exactly what we expect, so this is good. Now let's try d equals 3. And now we are shocked because we see we get a second order recurrence. And if we do even the next one, d equal 4, we get a third order recurrence. Also, the evaluation is as nice as it could be. It's a geometric sequence. It should satisfy a first order recurrence. So isn't this a contradiction to what I write here? Finds the minimal order. Of course, I don't put contradictions into my slides. It doesn't say it finds the minimal order recurrence for the sum. It says it finds the minimal order telescoper, and this is a difference. So the telescoper is a recurrence that comes with the certificate, with the antidifference on the right-hand side. And indeed, there is no smaller recurrence that satisfies this property. But the sum, by coincidence, indeed satisfies a smaller recurrence. And there's some very recent work by Mark van Hooy, where he has what he calls a submodule approach to explain this phenomenon a bit better. But so far, the takeaway message is just that with creative telescoping, you're guaranteed to find a recurrence. It need not necessarily be the minimal order recurrence that you get.
So, Christoph,
yes?
So on this example, the guessing idea that I suggested fails because...
Right. You can, of course, you can try, but then Gosper's algorithm will not give you an answer.
But in many examples, it would
work, yes. Okay, and last example, I take this occasion to give the definition of this hypergeometric function, but I guess most of you know this hypergeometric function. So here I again use the Pochhammer notation. We have three parameters a, b, c. We take their Pochhammers. We have this additional k factorial. And then we take the variable z to the k. So we have a power series whose coefficients are given by this hypergeometric term. And this is this famous 2f1 function. And many of the known elementary functions are special instances of this one. That's why it's very popular. And also this one we can do with these parameters. So here I put the Pochhammers. I apply Zeilberger's algorithm, and I ask for a recurrence in A. And you see it just works. We get a second order recurrence. Here we have A plus 1, A plus 2. We could do the same for B. Again, we get a second order recurrence in B. We can do with respect to C. And also here we get C, C plus 1, C plus 2, second order recurrence. Okay. I think, yeah, that's about Zeilberger's algorithm. Very quickly about the so-called Apagodo-Zeilberger algorithm. So again, we take f, a hypergeometric term, and we use this technical assumption that it is a proper hypergeometric term. And you want to write it in the form polynomial times a hypergeometric term, and you do this in a way that this polynomial is as big as possible. So you want to take as much out of this hypergeometric expression, and then you can write this h. It looks very complicated, but it's basically says that you can write it as a quotient of Pochhammer symbols. So here we have a Pochhammer symbol, and now because we have two variables, we have here n and k, and these coefficients here, they are integers, the hj and the hj prime. And we need 4 terms because in the algorithm you have to distinguish whether you have here plus or minus. Okay, and then these alpha, beta, gamma, delta, they can be whatever numbers, but in the index of the Pochhammer you need to have integers. So any hypergeometric term can be written in this form. So if you do that, and then somehow you once forever you run the algorithm symbolically using all these symbolic expressions. So the calculation is a bit of a mess, and I don't show it to you, but you have to do it once for all, and then you derive this result, namely that if you define R to be the maximum of the sum of all the hj coefficients plus the sum of all the dj coefficients, and similarly for the b's and the c's, then this is a upper bound for the order of the recurrence that Zeilberger's algorithm will find. And the proof idea is you write this thing, you go through the calculation, at the end you get your linear system, and you can show that if you choose R exactly like this, then you get a linear system where you have more unknowns than equations, and therefore you are guaranteed to find a non-trivial solution. This is the proof idea. And so this means, this is in the paper, the authors call it the Wittgensteinian ladder, that you have to climb once and then you can throw it away, because this calculation, actually you don't have to do this every time. You just have to remember the result and you can use it. So you can use this order, and it also tells you what in your answers, how you have to make your answers such that something exists. Okay, so this is kind of a simplification, and it saves you from the complicated Gosper subroutine in the algorithm. So you just make an ansatz for your telescoping equation and run the algorithm and solve a linear system. Good, I wanted to show this because in the second part of my lecture I will reference this quickly. Okay, so for today, this is the first half of the lecture, and I think time-wise it's half, approximately.
Yeah, but you can.
Yeah. Yes. Okay, so that means we can take a breath. If anybody has a question, that would be a good occasion. So that means, so the title of my lecture is Creative Telescoping for D-finite Functions. We have now achieved the first half. I told you what is creative telescoping. I still owe you explanation of what is D-finite functions. Good, then let's go. Lucia already mentioned D-finite functions, and I guess most of you, if not all of you, have seen this and know this, but nevertheless, let me repeat it so that we are all on the same grounds. A function f of x. Now we start with the differential case that so far I have put aside a bit. We only had looked at the summation case, the discrete case, but now let's go into the differential case. So f of x, a function in a continuous variable x, is called D-finite if it satisfies a linear ordinary differential equation with polynomial coefficients. And of course, we don't want that this equation reduces to 0 equals 0, so it should be a non-trivial equation of this form. Okay. The pi are, well, rational functions in x, or if you clear denominators, you can assume they are polynomials in x. So here are some typical examples. If f is a constant, of course, it satisfies this property x to the n, exponential, sine function, square root. All these are examples for D-finite functions. Why should we care about D-finite functions? They have some very beautiful features. It is a very important class of functions, and it is a very rich class of functions, as I shall demonstrate in a second. And some people call it holonomic functions. That's also fine. The next feature of this class of functions is that it's closed under certain operations. So when you add two such functions, the result will be again D-finite and so on. I will make this more precise on the next slide. And it is a very good data structure for doing symbolic computations, because it means, well, if you have such a function that satisfies such a differential equation, it means you can specify this function using a finite amount of data, a finite amount of bits. You have to store these polynomials in the differential equation, and you have to store finitely many initial values, because this is an order R differential equation, so you need R initial values, and this completely specifies your function with a finite amount of data. And together with these closure properties that we can do algorithmically, we can really compute with these functions in a very nice way. Okay, here's a list of D-finite functions. Of course, it's not complete, but somehow these are the most popular ones, let's say. So what do we see here? Cosine we know, cosine, hyperbolic cosine. Then here inverse sine, algebraic functions. And then there's this whole zoo of special functions, orthogonal polynomials and so on. So you see Airy functions, Bessel functions. Here is the hypergeometric function. Actually, here's the 2f1, and then you can generalize these to pfq, and all of them are D-finite. So really many functions that you meet in physics, in many branches of mathematics, they fall into this class. Of course, not everything, as we will see, but many things. So yes, talking about special functions, let me just say what I mean by that. So, well, a special function is a function that appears often enough so that it deserves its own name, and it cannot be expressed using the known set of functions. Like it cannot be expressed in terms of trigonometric, exponential, logarithm functions. If you meet such a function and it is of significant importance, then typically you give it a name, and then it's called a special function. So one instance I just mentioned are the Airy functions. They come from physics. If you want to know how in a rainbow the light is distributed, well, this is described by a certain differential equation. And it turns out that the solution of this differential equation you can compute numerically. You get a certain curve, but you cannot express it in terms of known functions, and therefore you give it a name and you call it the Airy function. And the definition of this function is being the solution with certain initial conditions of this differential equation. Well, and the same is true for the Bessel function. This appears in vibrations of circular shape like a membrane. Then these oscillations can be described by Bessel functions. And there are many, many others, and usually they come from physics, like Coulomb is from electromagnetics. As I said, they are solutions to differential equations and cannot be expressed in terms of elementary functions like square root, exponential, trigonometric functions. Okay. So now, as I said, there are closure properties for D-finite functions. So the theorem says if f and g are D-finite, then also the following functions are D-finite. We can add them, and of course subtract is the same. And the proof, actually, yeah, we do another proof, but now we are in another part. On the next slide, I do a sketch of the proof. So then the product of two D-finite functions is again D-finite. We can take antiderivative. The antiderivative of a D-finite function is again D-finite. And here the proof even fits in one line. You take the differential equation, you replace every derivative by the next higher derivative, well, and then it is a differential equation for the antiderivative. Also the differentiation of a D-finite function, the derivative of a D-finite function is again D-finite. This is not as easy to see, but also not difficult. You can do substitutions if you have an algebraic function, so function that satisfies a polynomial equation. You plug it into a D-finite function, the result will again be D-finite. And so if you play this game with the identity function, this implies that every algebraic function is D-finite. So algebraic functions is a subset of D-finite functions. Okay, so let's do the proof quickly. We have two functions, f and g, and we assume they are both D-finite, so they both satisfy a linear ordinary differential equation of a certain order, d1 and d2. And now we want to show that the sum, and we call it h, is again D-finite. So we shall show that there exists a certain order d that at the moment we don't know yet, and coefficients c0 up to cd, such that h satisfies such a differential equation. This is what we want to show. Now, we use the definition of h. Okay, we put the 0 on the other side. So that formulas fit more nicely. And then we replace h by linearity of the derivative. This is the f, the d's derivative of f plus the d's derivative of g. Here this one is not shown, and here this h is just f plus g. And now we use the fact that f and g are both d-finite. So if we have this d's derivative of the function f, we can use the defining differential equation of f to rewrite this high derivative of f in terms of lower derivatives. And since we assume that the order of the differential equation that f satisfies, we can always rewrite it in terms of f prime up to d minus first derivative of f. So this is written here. f prime up to d minus first derivative, and some coefficients that, well, are not important enough to deserve a name, so I just put a box here. But this rewriting process will introduce rational function coefficients. And of course we do the same for g. And we not only do this for this highest derivative, but for all derivatives. Well, I mean, here there's nothing to do because, well, this you cannot write in simpler terms. But you see in total, you get a big expression where you have derivatives of f up to d1 minus 1 and the derivatives of g up to d2 minus 1. So you rearrange everything, you collect coefficients, and that means you get a sum of the ith derivative of f, and this then now is multiplied by a big expression where, well, the variable x occurs, and all these c's here, they appear here. And similarly for the g, but they will appear linearly, so you can just solve this. Well, this you make coefficient comparison. Each of these coefficients must vanish individually, so this gives you a linear system, and you solve it. So it's really not magic. It's very simple. And then you also see like how you have to choose the d such that this linear system has a solution, and it will happen at latest if you choose d, the sum of the two, because then you get a linear system that has more unknowns than equations. So here from the ansatz you get d plus 1 unknowns, and here you see you have a system. This equation gives a system of d1 plus d2 equations.
I expected the max actually. I expected d to be the max of d1.
Yeah, it's also a good guess, but unfortunately it's not.
No, it's not because of the number of equations?
No, it's really this. Well, you see here we have
Hyperbolic sine. Yeah, some of it's mentioned.
yeah. I will also show in operators, maybe then it also becomes clearer. Okay, good, so end of the proof. Now it's time to wake up and to make a little quiz again. So here are several functions, and now it's getting more difficult. So I mean, hypergeometric is easy, but d-finite is more tricky. And again, I try to be very mean and design the examples so that I can trap you. Let's see if you get trapped. So I give you 1 minute to look at these examples. So the first example, who thinks this is d-finite? Raise your hand. Half of the people. Who thinks this is not d-finite? Nobody. And the rest is sleeping. Okay, good. The majority won. This is d-finite because, well, we have seen the exponential function is clearly d-finite. The error function is also d-finite. And here we do substitution of a rational function that is even nicer than substitution of an algebraic function, which we are allowed to do. And we take the product, so everything is fine. Second example. Again, who thinks this is d-finite? Raise your hand. 2, 3. Who thinks it's not d-finite? Yeah, more. And still, like 60% are undecided. This is not D-finite because of the little minus sign here. So actually what we do here is we take the 1 over cosine. So the hyperbolic cosine itself is D-finite, no problem. But if we take 1 over hyperbolic cosine, then this is not anymore D-finite because in general division does not work among D-finite functions. So that means, next example, learned that we should not do division. Yes. Here, exponential is an exception because exponential satisfies a first order differential equation, and in this case you are actually allowed to divide because also the inverse then will satisfy a first order differential equation, and then there's a substitution with the square root. This is no problem. So now it gets really tricky. That's true. So we should expect that this is not allowed. Yeah. And you're right. This is not D-finite, exactly for this reason. So this doesn't work. Now, last example. Who thinks this is D-finite? Okay, 5. Who thinks this is not D-finite?
I don't know.
Nobody dares, except Arlene. Here, yeah, this is, again, you could argue arctangent is not algebraic, so we would expect that this is not good. But actually here it is good because the derivative of arctangent is a rational function. So if you look at this exponential, you take the derivative, you get the same exponential times a rational function, and then you can make a relation. Okay? Let's look how this works. So for this purpose, I'm now using my package where we have this convenient function annihilator that analyzes the given expression and performs disclosure properties automatically. So when I give here this expression, it recognizes this is a product, and then it looks up the differential equation for f and for x. It does the substitutions and so on. So you don't have to type much. You just say annihilator and then of this expression, and you see here you get a second order differential equation. Here we have the inverse of the hyperbolic cosine, and well, the package complains that it is not recognized to be D-finite. You should be careful if you get this message. This is not a mathematical proof that this object is not D-finite. It just says, the package says, well, I don't know. I cannot compute it. Maybe for some strange reason it is, but yeah. Okay, then we had this thing with the log and the square root, and you see here you get a fourth order differential equation. Here we have the arctangent of x. Again, we get an error message, and here I'm proud to show you that this works, and you get actually this simple differential equation. So here the package is not trapped by this seemingly non-D-finite expression. Okay, as we have already seen in this demo, it is convenient to represent D-finite functions in operator notation. So in my talk, when I write dx, I mean the differentiation with respect to x. So if we apply it to f, it's f prime. If we apply it twice, we get d squared. And we apply it to f, we get f double prime. Well, if you take d to the 0, then it's just the identity. And I denote the ring of differential operators with polynomial coefficients, let's say with rational function coefficients, by this notation. Yeah, sometimes we use square brackets or angle brackets, whatever. It's just to remind you that this ring is not a commutative ring, because from the Leibniz rule, x times f derivative is x times f prime plus x prime times f. So you have this non-commutative identity in this ring. And to remind us, I use this angle bracket notation. Or more general, if you have dx times any rational function in x in this algebra, then it's r of x times d plus r prime for any rational function r. So we have seen all these special functions. One instance of very prominent special function family of orthogonal polynomials is the Legendre polynomials, and they are defined as solutions to this second order differential equation. They also depend on a parameter n that for the moment we can ignore. But so we have here p double prime, p prime, and p. And if we write this in operator notation, it becomes much simpler and turns into this polynomial. And so for doing computations, it is very convenient to write our equations as such polynomials. Okay, so we can restate the definition of D-finiteness. We can say f is a D-finite function if there exists an operator L in this polynomial ring of differential operators, and this should not be the zero element, with the property that L applied to f is 0. So this is just another way of saying that f satisfies such a linear differential equation with polynomial coefficients. So now let me restate certain facts that we have seen in the language of operators. So assume we have two D-finite functions, f and g. That means we have two operators, L1 and L2, that annihilate them. Then if we want to study the antiderivative of f, this is annihilated by the operator L1 times dx. And it's important that we have this factor dx on the right side and not on the left side, then it would be something different. So we first want to differentiate, then we get f, and then we apply L1 and we get 0. Now if we take the sum of f plus g, then in terms of operators, we should take the LCLM, the least common left multiple of the two operators. And actually, this operator L will not only annihilate f plus g, but actually any linear combination of f and g with arbitrary constants c1 and c2. And here's the proof. So if L is the LCLM of these two operators, that means there exists m1 and m2 such that m1 L1 is equal to L, or m2 times L2. So a left multiple, we multiply from the left for certain operators m1 and m2. Now if we apply, okay, and it's clear if you apply L to this, then you can apply L to f and to g separately, and because here we have L1 and here we have L2, it gets 0. Okay, and again here we see the LCLM. The order of this operator will be at most the sum of the orders of the two operators.
But any CLM would work. It doesn't have to be the least.
Sure, you can take a bigger one, but usually you want to be somehow minimal. And the last thing is just to say, if we have a function that satisfies an inhomogeneous differential equation, where the inhomogeneous right-hand side is a D-finite function, that is also fine. So L of f equals h, not 0, but we assume h is D-finite, then also f is D-finite because we can homogenize this equation. That means if h is D-finite, there exists an operator m that kills h. And if we apply m from the left to L, well, and we apply it to f, then this is L of f. L of f is h, and then m is applied to it, so then m times L is a annihilating operator for this function f. Okay, so this was about D-finite, about the differential case. Now we turn to the shift case, which is very analogous, so I think I can go quickly through this. This is, yeah?
I mean, the regular time was half past, and I
Ah.
you 10 more minutes because we started 10 minutes left, but it's already 10 minutes.
Thank you for reminding me. I had miscalculated in my head. Sure. No, then we should stop here, and
I think it's good because
reserved. Yeah, is a good point to make a break.
So.
Okay.
Yes, so if we have one or two quick questions for Christoph, and otherwise we can also discuss during the break, of course. Yes? Sure.
You had this theorem in the middle regarding some variant of Zeilberger's algorithm, which gave an upper bound on the order of the telescope, I think, if I understood correctly. Yes, this one. How does this change the algorithm? This I didn't quite understand. Do you just go straight to the max to this order, or?
Well, yeah. If you do this, first of all, you can save the step where you loop, so you could directly use this order. And actually, it tells you even more. You don't have to do all this Gosper form business, but it tells you exactly what is the right ansatz, what is the denominator and everything.
Other questions? Okay, so let's thank Christoph again for this talk.